there, kids. Dr. Division here, and today I'm going to talk to you about chi-square analysis and how you can use it in your biology class. You see, my biology teacher, Mrs. Magic, loves chi-square analysis almost as much as her beloved Diet Coke. Well, anyways, let's get right in there, kids. Chi-square analysis, as it relates to your biology class, is a way to check if the variable you modified has had any significant change on your data, or if it's all just random. Well, isn't that fun? Well, kids, this here is the basic chi-square analysis formula. And on the right side here, we have x squared. That's our chi value. That's what we're looking for solve for. Here we have the summation sign, which lets us know we have to add up all our results to get our final x squared value. On the top, we've got observed minus expected squared over expected. Observed is what you see in your experiment, what actually happened. And expected is what you would expect to happen in a theoretical standpoint. Well, next up, kids, is example 1. We're going to see how this thing works. Isn't that fun? Well, hello, kids. In example 1, we're going to roll a die 36 times. And as you know, a die has 6 sides. So, we have each possible roll could result in one of 6 numbers, which we've listed here. A 1, a 2, a 3, a 4, a 5, perhaps even a 6. Personally, I like to roll snake eyes. You get to roll again. That's stealth time. Here, we have our expected values. If you roll a die 36 times, there's 6 possible options. You would expect each option to be hit 6 times. So our expected values for all 6 is 6. Now, my assistant rolled that die 36 times off camera, and these are the numbers she came up with. A 4, an 8, a 3, a 5, a 9, and a 7. Now, using these numbers, we're going to plug them into our chi-square formula, and we're going to find out if the way she was throwing the dice perhaps manipulated the values, or if they were truly random. Alright, we'll be right back with that, kids. Well, alright, kids. What I've done here is I've gone ahead and done 3 of our chi-square formulas. So that's half of the results we're going to have to do. So, for x sub 1 squared, we have our observed value of 4 minus our expected value of 6. Now we're going to square that and put it over 6. If you do that arithmetic, you'll get a final answer of 2/3. Now, as you can see, I've repeated the process for x sub 2 and x sub 3. What you're going to have to do is x sub 4, x sub 5, and x sub 6. Now, when you've done that, add them all together and see if you get the answer I did, which will be coming up right after the break. Alright, kids, so I've done the math here, and all of our x squareds come out to 14/3, which comes out to 4.666 repeating. Now, we want to make sure we have the decimal value for x squared so that we compare it to our chart of values, which you'll see here in just a second. Now, first things first, we have to explain degrees of freedom, which is how we're going to read the chart. Degrees of freedom is equal to the number of possible outcomes minus 1. So in this situation, with 6 possible outcomes, our degrees of freedom would equal 5. So let's make sure when we look at this chart that's coming up here in a second, we're looking at 5 degrees of freedom. And then we'll decide whether we can accept or deny the null hypothesis that would state that the actions were truly random, or if my assistant's throwing and somehow modify the results. Alright, we'll be right back. Alright, kids. Well, what you've just seen is a fully fleshed out chi-square analysis table. That's for if you're doing this at home on a different problem. What I've drawn here is a more concise version, just for our little experiment. Now, we've got degrees of freedom, 1 and 5. We're going to use the 5 because our experiment had 5 degrees of freedom. And here we have our p-value, 0.05, which is to say there's a 5% chance that this is incorrect. So we are 95% sure of what we're saying, which is the generally accepted number in the scientific community. Now, with 5 degrees of freedom, for it to have been a non-random result, we would have needed our x squared value to be 11.07 or greater. As we can see here, we had an x squared value of 4.6 repeating, which is significantly less than the 11.07 we needed, which means that we have to reject the null hypothesis and state that our experiment was in fact random and the results were in no way affected by my assistant's faulty dice throwing. So, in the scientific world, that would mean that the results are likely to not be repeatable and that the experiment, whatever it may have been, has not produced a significant result. Now, after the break, we're going to talk for a moment about the significance of chi-square analysis in the real world. So, stick around. Alright kids, our final little segment here. We're going to talk about the real-world significance of our chi-square analysis skills that we've just gained from this video. Now, as you can see, there's nothing on my board, so I'm just going to talk to you about it. In the biological world that you're in your class, you can see if the two options you presented to, say, pill bugs had any significant change on their movement patterns. We would just take our results and plug them into the formula that we used earlier. However, outside of your biology classroom, in the real world, pharmaceutical companies use chi-square analysis all the time. Now they use it to ensure that their drug trials are producing significant results and that their drugs will be effective. They will put their results into our formula, the same one you just used today, except they do it on massive scales with hundreds of thousands of data points. So, as you go forward in life, if you decide to become a scientist, don't you forget about Dr. Division and this little chi-square analysis lesson here, as it could serve you very well. As you know, the pharmaceutical company, they make big bucks, and they even might produce a little Diet Coke for Miss Madge over there. Alright kids, see you next time.